All right, I have talked about in my life having superpowers of high resolvability. It comes from my near point being so close to my face. I can get things up really close and personal to be able to see them. So when we deal with a circular aperture, which is just a fancy way of saying a hole, when light from an object goes through it, it has a diffraction pattern, right? This is a lot like a single slit, right? The only difference is instead of it being one-dimensional, it's round. So it'll spread out in multiple directions. So when this hits a screen or something, we would see a circular oriented diffraction pattern. If you have two light sources that go through the same hole, and here they are separated by some angle theta, this one also casts a diffraction pattern. And we see some overlap between these two, and that's interesting. What if we bring this to where this angle is so small that the patterns look like this? Here's pattern one, and then for your benefit, I'll make the other one a different color. Let's say pattern two is located here. And the point being, bright spot 2, central maximum, occurs inside the first diffraction minimum, or the dark ring around the first one. That results in a composite image that looks like this. And I don't see two patterns there. I only see one. This is what we call not resolved. In order for things to be barely resolvable, we have to satisfy Rayleigh's criterion, which is just that the angular separation of these two things has to be large enough to pry these two diffraction patterns apart so that they don't do this. And that situation comes at 1.22 lambda over d equals what? This angle. If you want something to be barely resolvable, this angle has to be equal to this value or higher. All right, a bigger angle is fine. This is the diameter of the aperture. This is whatever wavelength we have, and the 1.22 is just some corrective factor that comes from calculus or some other kind of math. Rayleigh's criterion is typically for very small angles, so it's kind of implied that this is also related to tangent of r. So oftentimes we don't know really what is the angular separation. More often than not, we know kind of what is the linear separation. Maybe I'll call that delta y. Real questions about this could be, how close must I bring something for it to be fully resolvable? And for us, let's call this distance, I don't know, maybe big L. If we were to do this in Rayleigh's criterion for any color, let's say we've got red giants in the sky, stars or something like that. So I've got two red stars, they're really close together, and we want to know, are they resolvable? I would take whatever their wavelength is, so let's say 650. I take D. What's the D? That's the thing that I'm using to look at it. It can be the pupil of my eye, or it could be the size of a telescope lens. And that's why we use telescopes. It has less to do with the magnification and more to do with increasing the size of the hole in the lens or the mirror to collect that light and then pull these diffraction patterns apart. So that would be just that, the diameter of the aperture. And then how do we deal with the tangent? Well, that's fine. If we know how far apart they are and we want to know how far away it is, we would say that tangent, I guess, is delta y over L. Oftentimes you want to be able to resolve things. So like in my situation, if you got really fine details printed on the back of your driver's license or fine details on coins. You want to bring these things closer such that if they have the same angle or the same linear separation, the features, but we get them closer to the eye, that really wrenches this angle upward, right? Makes it bigger. And that makes these things resolvable. But what if you have to get it so close to your eye that it's closer than the 25 centimeters that would be true for most people's healthy near point? You'll never be able to see it without a magnifying glass or something to make the features bigger, so that they're spread out more. I don't have that problem, right? We found out that my near point is about 10 centimeters in front of my face. So I can bring these things 3 times closer almost, or maybe about twice as close. And it gives me this ability, right? So I can separate these out and see them. Other realistic cases where you would do this, it would be the question of, is this a motorcycle or a car that I can see in the distance? Does it have 2 headlights or does it only have 1? If it's got 2, you won't be able to tell because they look like they're not resolvable. So this vehicle would have to get closer to you before the 2 lights started to separate out. So that's a realistic case. Another one might deal with having a TV. Sometimes you don't want to see these fine details. So in the TV, we've got pixels, as we know. So let's say here's some of the reds. We've of course got the greens. And somewhere I guess there are blues. And I guess we use this technology that puts them in triangles. So a question that comes up is, do you really need a 5K TV or 5K monitor? They're super expensive. Could you get by with a 1080? Could you even get by with a 720p? Right? So what we want to think about in this case is not being able to resolve it. So if this is your eye with a known aperture size, and you have these 2 pixels that are separated by some distance, let's say the red ones, we might ask a question like, realistically, if we're in a dark room where D is maybe, let's say 5 millimeters, how close do you have to get to be able to see these 2 pixels? And you don't want to be able to resolve them, right? That's the point. One of the most frustrating things for me is I'm playing Fallout on a 7-foot projector, and the pixels are so big, they're probably about as big as these grid marks on the paper. So it really sucks when you've got a high-def game on a modern console and it looks like Super Mario Brothers from 1985, right? It's just irritating. So, do you really need this high resolution? You have to sit far enough back away from the TV to allow these pixels to blur together. So I think there's a problem on canvas to try out. Look at that and just practice with it, right? Sometimes you want to resolve, like with the motorcycle and the car. Other times, hey, you want these things to blend together, right? It's what happens with newspapers. Actually on paper, if you've ever seen one, look really closely. All the graphics are little dots, right? They're kind of pointillistic and they're not aqua colored. It's because you can get by with less ink and the brain will fuzz these things out and the eye will fuzz them out to kind of fill in the gaps of what's not painted.